In this video, I'll be going through some worked example questions related to circuitry. Questions come from paper 11 from 2019. This was summer administration from May, June. Question 33 reads, a voltmeter connected between 2 points P and Q in an electrical circuit shows a reading of 1 volt. Which statement is correct? Is it the energy needed to move 1 coulomb of charge from P to Q is 1 joule? The energy needed to move 1 coulomb of charge from Q to P is 1 joule. The energy needed to move 1 electron from P to Q is 1 joule, or the energy needed to move 1 electron from Q to P is 1 joule. Let's remind ourselves of the definition of voltage. Voltage equals energy per charge. So 1 volt is really 1 joule per 1 coulomb. To move something, to move a charge that is positive 1 coulomb from from P to Q, does that require any energy? Because it's positive, and this is a positive sort of, terminal here, it's going to repel. And so it doesn't cost any energy to do that. Rather, it takes energy to move something against the electric field. And so this is kind of like what a battery does. A battery has a positive terminal and a negative terminal. And we hook it up to wires, and there's, a light bulb in there. Okay, some source, right? Some resistance, right? So we don't have a short circuit. Electrons are repelled by this negative terminal. They go around the circuit, they power our light bulb, and they pile up here at this sort of positive end. If there is chemical energy inside of the battery, that chemical energy does work to move those charges this way, back to the negative end, where they can then go back around the circuit. So that's what keeps our light bulb sort of shining, is the fact that there's still, chemical energy left in our battery. And so we have to spend energy to sort of move the charges against the electric field. Otherwise, they're just sort of, being repelled anyway. And so I'm leaning towards this answer, right? The energy needed to move it's not 1 electron, because 1 electron has how much charge? Not this, right? A volt is 1 joule per 1 coulomb, right? That's how we sort of define the unit of a volt, 1 joule per coulomb. So coulomb is sort of what we need. That's the charge we need if we're going to get 1 joule of energy up here. They already tell us that, there's a 1 volt potential difference. And so we're sort of thinking about how much energy. It's not 10 to the negative 19 coulombs, 1 electron, it's 1 coulomb. And so we can eliminate choices C and D, because the electron isn't the correct charge, this is. And so it's just a matter of saying, well, energy is needed to move it from negative to positive, right? Like, so if the charges sort of pile up here, then we have to have sort of chemical energy in our battery or whatever, our hand crank generator, some source of energy to move this way. And so I like from Q 33B. Which graph best represents the variation with current I of potential difference V for a filament lamp? So remember that we're looking at V against I, not I against V. We see like the IV characteristic of a filament lamp looks like that. Okay. That's the IV characteristic, which looks like this curve here. So if this is the curve that we would expect for an IV characteristic, meaning that as we increase the voltage, we're not getting sort of the same jump in sort of current that we were getting, because there's a lot of heat that's just sort of being created. That's what an incandescent sort of light operates on. then we'd be looking to sort of, translate this kind of a plot so that this axis is here. And so that's going to agree with, I think, graph B, right? You just sort of inflect it. So instead of it sort of leveling, like what would happen if we went this way? Well, now here we're getting big changes in current, okay, or tiny changes in voltage, or rather, let's look at here, we're getting, for a big change in voltage, right? So like there's the change in voltage, we're getting a tiny change in current. So here we've got the same thing, a big change in voltage, right? And a tiny change in current. So like this graph here, which is the correct IV characteristic for a filament lamp, gives us this I characteristic. And so just kind of the inverse of this is that. When a battery is connected to a resistor, the battery gradually becomes warm. This causes the internal resistance of the battery to increase whilst its electromotive force stays unchanged. As the internal resistance of the battery increases, how do the terminal potential difference and the output power change, if at all? So here we've got the terminal potential difference is equal to the EMF, but if there is current that's being driven through the battery, then there's some lost volts, I times R, where this R is the internal resistance. And so that's what it's saying, like it becomes warm. Those are the lost volts, right? The lost volts is like the source of this heat energy. The battery itself is getting warm because we're sort of losing some volts. Not all of the EMF is available to the external circuit. As the internal resistance increases, they're actually saying like this is actually getting bigger and bigger, okay? How do the terminal potential difference, and so that's this quantity, and the output power change? All right. If there's more and more resistance in the battery, then we're going to lose more and more volts. And so if the EMF stays unchanged, which they say that it does, but this is going up, then the lost volts increases, meaning we're going to lose more volts. We subtract away more lost volts from our EMF. Sometimes it's helpful with numbers, like a 9-volt battery, and let's say we're losing, 1 volt at first, then we lose 2 volts, because this increased. Well, the terminal PD has less and less EMF, sort of available, right? We're losing more volts. And so to me, it seems like this would have to decrease, right? It's not going to change. Now, how about the output power? Output power, current times voltage, or connected to a resistor. So we could think about, okay, the output power in this resistor, I squared R, V squared over R. So if V goes down, okay, R doesn't change its value. It's still the same resistor, but now there's less voltage available to it. And so as the voltage goes down, what's got to happen to the power? It's got to go down too, right? Like this is less and less. We're dividing by the same number. So the power's got to go down too, right? I think it's A for that reason. But sometimes I get a bad feeling about certain questions. Like I got a bad feeling about there's like a bow and arrow question that we did in 2013, and I finished the the calculation didn't seem so troublesome. In fact, maybe that's why it gave me a bad feeling. It's like, oh, it seems like there's something we're missing here. Like is it really this straightforward? And sometimes you overthink a question, which is maybe what's happening here. So it's perhaps that just like with some mistake, we're incorrectly choosing A, and there's just something I'm not thinking of. That can happen. But I feel pretty good about A. We'll give ourselves feedback in a moment here and see if we need to revisit our thoughts on this at all. So 35, I said A. 33, I said was B. I forgot what I said for 34, but remember it. B for that one, right? So 33B, 34B, 35A, and the request was for circuit questions. We might have one or two more circuits, sure. 36 and 37. 36 is a cell is connected to a resistor of resistance 3 ohms. The current in the resistor is 1 amp. A second identical resistor is added in parallel. The current becomes 1.93 amps. What are the EMF and the internal resistance R of the cell? I was trying to do the same thing and just look at the answers and see if I could just solve it that way. I feel like, yeah, I mean, I should have learned my lesson. Just do the calculation. We got one wrong by doing that last time, but trying to be clever. All right, so let's go through it. It's connected. This resistance, we got this current. So we've got a source of EMF hooked up to an internal resistor, or there is internal resistance in the battery, so it's hooked up to it. Circuit comes around like this. Got another external resistor going around like that. We know the value of this is 3 ohms. We don't know the EMF. Okay. We don't know R. But we do know that the current that's going through this resistor is 1 amp. Okay. So V equals IR, and we know that there is 1 amp of current, and we know that there is 3 ohms of resistance here. We could calculate the voltage drop across this, and that's going to give us V, the terminal PD. In other words, this resistor only has the terminal PD available to it. It doesn't have the EMF. It's the EMF minus the lost volts, which give us the terminal PD. All right, so we don't know what this is, but we can calculate V equals IR with 1 amp of current, with 3 ohms of resistance. There must be 3 volts of terminal PD. We can then say 3 volts equals the unknown EMF minus the current is 1 amp times what value for R here. So there's an equation. A second identical resistor is added in parallel. The current becomes 1.93 amps. Okay. Now that's kind of tricky because the way I read this, it says the current in the resistor is 1 amp, and now it says a second identical resistor is added in parallel. The current becomes 1.93 amps. Can we read that as the current through that same resistor, or this is like the current in the whole circuit? If we solve it like the way it's worded, which makes it seem like the current in the resistor is 1, the current becomes this. Well, it seems like the current in that resistor becomes that, and so we could take 1.93 amps times the same 3 ohm sort of resistor there. And here we're getting a terminal PD of 5.79 volts. What EMF minus now it's 1.93 R. So let me rewrite that a bit more clear. 5.79 volts is V equals E minus I R. And this equation, 3 volts equals E minus 1 third R. So here we've got 3 equals E minus R. If you add an R to both sides, then we get an equation equals 3 plus R. And we could substitute that in over here. In other words, 2 equations with 2 unknowns, that's what you need in order to solve. Because both R and the EMF are unknown for any given equation, that's why they had to sort of give us this second bit of information. So now I could say 5.79 volts equals 3 plus R minus 1.93 R, because E is, I think it's 3 plus R from this equation, 1 R. So 1 R minus 1.93 R's is negative 0.93 R. And subtract 3 from both sides, so 5.79 minus 3 is 2.79. All right, so I just combined some like terms here. I have 1 R minus 1.93 R is negative 0.93 R. Subtract 3 from both sides, 5.79 volts minus 3 is 2.79. So now I got my 2.79. I'm going to divide it by 0.93. And that actually gives me an internal resistance of 3, which is not any of these answers. So that's no good. We got our EMF, got our internal resistance bar. So by putting another resistor in parallel, we draw more current from the battery. So I think from this, where did we go wrong here? I think we had, when we plugged in the 1.93 for the current, we're looking at that as this is the current that's sort of going through the battery here. And it may not be the case, right? Because they say, I think I said like the current becomes 1.93 in the resistor. So it's like this went from being 1 to 1.93. Well, then there should also be 1.93 amps of current going through this 1, 2, because these have the same resistance. And so the same sort of current would be drawn sort of through each one. So we could say if they're telling, and again, I guess it's not that clear like the way that it's worded here, the current becomes 1.93. That's not saying the current here, but rather the current here through that 3 ohm resistor where it used to be 1. So I don't know if we need to use Kirchhoff's first law, which just says like if there's 1.93 amps through this one and 1.93 amps through this one, then what's the actual current that's sort of going through the battery? It's going to be, you know, the charge that goes into a point comes out of it. So it'd be sort of the sum of both of those currents, 3.86. That just doesn't seem right, you know, like that we increase the current sort of by that much. I really don't like the way this question is worded at all. Anyway, if we did this, then we'd say, 1.93, I'm sorry, amps. V equals IR. And so we still have that current going through 1.93. So we still get 5.79 volts, and that's the same voltage across both sort of parallel branches here. So that doesn't change sort of that. But now, if we said there's 3.86 amps going through R, and our first equation, which is before we sort of had this parallel branch, it told us that the current in the resistor was 1. Now there, it's very clear that there's only one path, and so there's only one place the current can sort of exist. Here, I'm guessing it's like the current becomes 1.93. The current in the circuit, the current in the resistor, which is kind of the way the sort of the wording sort of makes sense to me, that the current in the resistor is this, the current becomes this. Well, it's kind of like in that resistor, right? So our first equation was the 3 volts equals E minus R. We have this one. So I think it's still good to say, well, E then is 3 plus R, right? Add R to both sides. 5.79 equals 3 plus R minus 2.86 R. So then you subtract 3 from both sides, and you know, like all we did was sort of change the. I want to put 2.86. Oh no, 1R minus the. I can't make a mistake like that. 2.79 divided by 2.6. Still isn't an answer. If you look at these two here, if the EMF were 3.04, and this were the internal resistance of the battery, then for the initial sort of conditions where there's 1 amp of current, V equals E minus IR, then 1 amp times this internal resistance is just enough lost volts to subtract away from this EMF to give you the 3 volts we know we have, right? Because we still have V equals 5 times R. So we're going for 3 volts. But so too does this, right? Like this gives you the same sort of answer where if the EMF were 3.11, the internal resistance for this, also 1 amp would sort of work to give you the 3 volts. And so at this point, it's really just sort of figuring out the answer so that I know what they mean by this word here, because it's not very clearly worded in my opinion. And maybe, you know, there's some better way to sort of interpret it. So if we then take a second identical resistor is added in parallel. So the circuit resistance becomes this. 1.93 times 0.113, 0.21809. Four. So if the current became 1.93 and the circuit resistance was 1.5, then the new potential difference is 0.5. We did 3.11 minus 1.93 times 0.113. That gives us this answer. But if we did 3.04 minus 1.93 times 0.0358, that does not give us this answer. And so C is the correct answer. I'm sure of it now, not 100%. But I feel like my brain turned to mush a long time ago, and there's a much more clear way to sort of see this that I need to take a break and then come back to it. So I go, oh, come on, this is this. And so I think, yeah, like a system of equations would certainly solve it, but we just have to make sure we've got the right values sort of going into it. And then we just sort of go through this roundabout way that I've done here. I'm going to circle back around to this one, keeping in mind that C is the answer that I sort of come up with when I work through it the inefficient way. Well, that was tough. I don't think that was, oh man, we have another one. What happened to our radioactivity? A battery with negligible internal resistance is connected to 3 resistors as shown. All 3 resistors have the same resistance. The current in the battery, see how clear that is? The current in the battery is 0.3. Okay, what is the current in resistor X? This one I can just kind of see the solution is this, all right? Because if there's 0.3 amps and all of these have the same resistance, then I kind of know like in this path down here, there's twice the resistance of this one. And so the charges, like twice as many charges will go this way as that way. You also have to keep in mind Kirchhoff's first law. So we have I, which is this current, is equal to I1 plus I2. And then we also know that like the current, so if we call sort of this branch I1 and then this branch I2, and we also know because there's twice the resistance to the flow of charge, there's going to be half the current, right? Like this branch resists the flow of charge, the current, twice as much. And so we could say that I2 is going to be half of I1, or we could just say if we did 2 times I1, we'd have I2, right? If we just, oh no, did I do that right? Double this current to get that one, sorry. 2 times I2, right? Because there's half of the charge flowing through this, twice as resistant, so there's half the current. So if we double this current, we get this one. So it's I1 equals 2 times I2. And once again, I think if you've got a system of equations like that, you could plug it in and solve it more formally, but I just kind of know, well, if I have to add up to 0.3, and I also need, a number that's twice as big as the other one, then 0.2 is twice as big as 0.1, and those are numbers that add up to 0.3. So I can just kind of, see, well, this is a 3, and there's, 0.2 going that way, 0.1 going that way. So the answer here is going to be 0.2. And then you could, plug it all into these equations and see it work out to do that a little bit more formally. The diagram shows a potentiometer and a fixed resistor across a 12-volt battery of negligible internal resistance. The fixed resistor and potentiometer each have a resistance of 20 ohms. The circuit is designed to provide a variable output voltage. What is the range of the output voltages? We could potentially drop this thing all the way down to 0, right? So in other words, if there's 12 volts here, then 6 volts drop across this and 6 volts drop across this because they're the same value. All 12 volts drop. If we put like this slider all the way down to here, then we have no output. In other words, we dropped all of our voltage. So 0 is a possibility, okay? So we can eliminate choices C and D. This thing could go all the way down to 0. Now, if we slid it up to here, though, then what we'd have is 6 volts dropping across this resistor, and then we'd still have 6 volts sort of, again, it would drop across this, but there's also going to be this parallel branch now, right, that also has 6 volts, so remember that in parallel branches, the voltage is the same everywhere. So this thing could go as low as 0. If we move this down to here, if we moved it up to here, then we'd have 6 volts available. So from 0 to 6 would be the range of output voltage. Now, I really feel like that's the best way to interpret it, but it doesn't give you the right answer, so I guess there's a problem with that. I mean, the current becomes, say the current in the resistor is this. The current becomes this. To me, that seems like, well, that's the current in the resistor now, the way they worded it. But if you solve it that way, you get like 0.97 for this. Clearly not right. 33, we said B. Good. 34, we said B. Good. 35, we said A. Good. 36, we eventually got a C there, but that was the one we were just looking at again. 37 was C, and 38 was A. I forget about those. 37 C, 38 A. Yep, 37C, 38A. So good. I mean, we got them all right, but this question here. I think this is it. I think if I work through this, it will give us the answer. You know, it's like I think I already worked through this. Say that plus R. I think I didn't have this right. Plus R minus R, so negative 0.9 R equals, there we go, negative 2.895 minus 3 is a negative. The negatives will cancel. 0.105 divided by 0.93. You know it, 0.113. And then once we substituted that back in, we have it. So my apologies to everybody for sort of going on that Dr. Schleif's wild ride to internal resistance in this battery here. We got the answer, you know. And again, I like this word, times 1.93. So this is the current in the entire circuit, okay? So we can say, well, what's the voltage then? V equals IR. You do have to calculate what the circuit resistance is. So if you say, well, this is the circuit resistance, if this is the current in the circuit, then I can calculate what the terminal PD is just using Ohm's law, V equals IR. So once you've calculated the resistance, then you kind of know 2.895 volts, that's the terminal PD for the second setup, the parallel circuit. And again, it kind of makes sense that if we put resistors in parallel, we draw more current from the battery. So this number goes up, you know, and we're also driving more current through the internal resistor. So we're going to lose more volts. And so if initially we had 3 volts, but now we only have 2.895, that also makes sense that we're losing more volts. So the terminal PD would go down as we draw more current from the battery, as we drive more current through internal resistance. And so that's a very reasonable value, which is why as soon as I had this equation, it seemed right to me. And then if you just go through the working, you get a good answer there that we already know is correct, because I solved it sort of using this, but in a more sort of less straightforward fashion. So there really are some kind of trickier questions, but if you size them up, you know, you don't sort of fall down the rabbit hole of letting your thoughts sort of, you know, so, oh, well, maybe it's this, and then it's easy to sort of, you know, get sort of mixed up, and then you kind of have to kind of reset, and you go, well, wait a minute, what do I really know here? And, you know, kind of let me make this a little more clearly. Then there's a really straightforward way. So it really is just a system of equations. We kind of knew that was a valid equation. There's our other valid one. You just have to have the correct terminal PD. So I think I had like a value of 5, so I don't know what I was doing, but I made some sort of error there. If you see a more clear way to go about the calculation, leave it down in the comments below for me. This has been another set of work examples with Dr. Schleif. We'll see you next time.